Hello. In this video, we're going to talk about composite functions, also known as nested functions. Maybe you've heard of a nesting doll, like this one. Right? So in a nesting doll situation, remember that there's a doll within a doll, and sometimes there's even multiple dolls, like in this particular case, another doll, and yet maybe another doll within that. Oh my goodness, there's another one here. And then we finally have our last little tiny, tiny, tiny doll. Or if you don't remember those, maybe you've seen a little yurt. You've seen these before? You have a house within a house. Let's grab another house here. Within another house. Within another house. They have these in Central Asia where I used to live. Okay. So in these situations, we have something inside of something else, right? It's nested. So something within something else within something else. Similarly with functions, oftentimes we have a function inside of a function inside of another function. Why would we ever do such a thing? Well, think about in real life, right? Typically with the function f of x, we're saying that this function depends on this one variable x. But in life, things aren't that simple, right? Sometimes a function might be talking about how much money you're going to make in a certain year, right? And that depends on maybe the type of job you have. And that might depend on the education level that you have, which might depend on how you were raised. And there's many things which end up contributing to that output, right? Similarly, we're going to talk about f depending on g, depending on h, depending on x. So let's get started and maybe grab yourself a doll so that it makes more sense. So to begin, I want to look at this situation where we're talking about values like x, which are being kind of mapped into another function called g of x. So g takes on values of x as inputs and produces an output. But what if that new output generated another function? In other words, f of g of x. So when I see f of g of x, what that is saying is f depends on g, which depends on the input x. Okay, so I won't do 5 of these in a row, but let's just do a few. So suppose we have f of x equaling 3x plus 2. A nice linear function. So I know that f depends on x, and it's a linear growth of 3 units every one x value. And then it goes starting, of course, at 2. But we notice here that we have another function, which has a different type of growth. It's still linear, but it's growing a little slower, because the slope is not 2, but 1. G of x equals 1x plus 5. So if someone were to say that f depends on g, one way that they could do that is this way. On the left, it says f depends on g, which depends on the input x. So the very first thing you would do if you were trying to interpret this, and you have the equations like they're presented here, you would first say, I'm going to go to my f function, but replace every input not just with x, but with what it depends on, which is g of x. So in the f function, I'm told to do what? I'm told to take 3 copies of my input and add 2. But now my input is no longer x, it is g of x. So this is my new input. My new input is g of x. So that's what I input into the f function. So basically, g lives inside of f, right? Because f depends on it. So we're going to say here that we have 3 copies of the input, g of x, or x plus 5. So I input that. And then I'm supposed to add 2 to that. So now we just do algebra, right? Distribute and add, like terms. 3x plus 15 plus 2 would be 3x plus 17. Notice what happened. When f depended on g of x, we got another linear function, but this time our initial y-intercept where we begin is not at 2, it's not at 5, but it's actually at 17. So this is going to grow a lot faster because we're starting at a different level. We're not starting at 2 or 5, we're starting at 17 and then going up 3 units every one input. On the other hand, what if we had a situation where our model was actually that g depended on f instead? Oops, there we go. If g depended on f, we would start with the g function instead. So we'd start with our g function, which says take your input and add 5. Now, if our input this time is f of x, which is here, we would input f of x, which is 3x plus 2, anytime we see an input x in our g function. So if you want a shortcut, what you're really doing is replacing x in the outside function with whatever the inside function is. One more time, you're replacing x in the outside function with whatever the inside function is. So that's what's happening right here. We're saying instead of the input x, replace it with f of x, which was 3x plus 2. That was our f of x. Now I do basic arithmetic. Add my 2 and 5, I get 3x plus 7. It's still a linear model, right? But the starting place now is not at 5 or 2, but rather at 7. Okay, Let's take a look at one more piece of information on this screen. We noticed that in each case we had lines to begin with, which are a type of polynomial, right? There's no fraction to worry about denominators being 0. There's no square root to worry about negative radicands under that square root symbol. So the domain of the original lines, polynomials in this case, is just negative infinity to infinity. Oops, get a parenthesis going on there. Negative infinity to infinity would be our original domain here for each of those functions. So what does that mean for our new functions? Well, if you had an original function which had any input, and you put it inside of another function which had any input possible, the output, the new function if you will still allow any input. The only way we need restrictions is if the new creation has a fraction, a denominator, or a square root, or if the function that we first depended on had a square root or a denominator. So we're going to look for restrictions, but in this case, if they're both polynomials, you have nothing to worry about. There are no problems. There are no restrictions. Okay, so let's practice f of g of x, g of f, f of f, g of g. Let's take a look at our next slide. Suppose you have a linear function again, that f of x equals 3x plus 2. So that would be this guy, okay? And g of x equals 2x squared minus 1. Okay? So we could put one function inside of another, like f of g, g of f, but did you know we can put a function inside of itself? Yeah, we can actually say that the function depends on the same type of function. That would be like f of f, or g depends on g, okay? So don't be surprised or alarmed if you see something like that. Now, one of the things that you'll see in some textbooks or online software is instead of using parentheses to say f of f or f of g, they might use an open circle like this. And when you see the open circle, it's not multiplication. It really is saying composition, okay? I like to think of the little O that's floating around there as an O in the word composition. There's a couple of them actually, but whatever helps you remember it. This means that I really have f, the outside function, parentheses, the inside function of the input, which in this case, x is 4. Okay? So if this is the situation, f of 4, what that's really suggesting, I'll try to be color coordinated here, f was red, right? f of 4. What that's really suggesting to us is that we would say my f function depends on the f function itself evaluated when x is 4. So you could do this in one of two ways. You could either begin with the outside function, plug in the inside function, the nested function, f of x, and finally replace x with 4. But most people will probably start inside here since we have a number. So if I have a number inside, that's typically where I'm going to recommend you start, if you have a number instead of x. So let's find f of 4. Let's start there, finding f of 4, and that will make your life a little bit faster, a little bit easier. So what would f of 4 be, just using basic algebra? Yep, that would mean plug in 4 to the f function as your x value. So that would mean 3 times 4 is 12, and 12 plus 2 is 14. So if you said f of 4 is 14, you are correct. So this would equal something depending on the number 14. Now what was my outside function? It was f. So now f depends on 14. In other words, evaluate the f function when the input is 14. So go back to your f function and say now it depends on x being 14. So this would mean 3 copies of 14 and then add 2. Okay, so if I take 3 copies of 14 and add 2, what do I get? That's right. If you take 3 copies of 14 and add 2, you're going to get 42 plus 2, or 44. So now we know the answer by doing f of 4 first, and then taking f of that number. So the answer would be, when f depends on f, which is inputted at x equals 4, we end up with an output of 44. Now, if you didn't like that approach, feel free to find f of x, and then just replace x with 4. Both ways work. Okay, try to pause the video and do the next one on your own. It says g of f of 4. So the g function, I'll use blue for that to be consistent. The g function is depending on the f function, which is the red function here, and it's being evaluated when x is what number? That's right, when x is 4. Okay, so if we're evaluating when x equals 4, I think we already did that earlier, right? We evaluated f of 4 above, and what did we get when we plugged in 4 as the input of the f function? That's right, we did 3 times 4, which was 12, and 12 plus 2, which was 14. So we already knew this was really 14. So simply we have g evaluated at 14. Maybe you already figured that out and you're a step ahead of us. That's great. So what does that do? Well, it means that we go to the g function and we evaluate it at an input of 14. So the g function, which was my blue function here, it was actually not a line, but a parabola, right? Degree 2 means a quadratic function here. So it tells me to take 2 copies of my input squared and subtract 1. Why? Because it's the g function in the outside. Okay, so I need to take my input and square it. My input here is 14. So if I take 14 and square it, order of operations, we do exponents before we multiply. Try PEMDAS or BIDMOS if you're from overseas. 14 times 14 is 196, and if you multiply that by 2, you get 392. If you take 392 and subtract 1, we have 391. So feel free to pause that if I lost anybody. Feel free to go through that again. Okay, so the output when g depends on f and f depends on the input of x equals 4 should be 391. Again, if you haven't already tried this, pause the video and do one of these on your own. The next one says f depends on f evaluated at 1. So I would start off with the blue function f depending on the inside function f, but evaluated at the x value of 1. Well, this is different than last time. A couple reasons. One, we have f of 1 inside instead of g of f, we have f of f again. So f of 1 would mean go to the f function, which is our blue function, and replace the input x with 1. So that means 3 times 1, which is 3, add 2 to that, and you get 5. So this means that this input is really just a 5. So now I'll simply need to evaluate my f function at x equals 5. So go back to that blue function f, and that was the linear model 3x plus 2. So I take 3 times the input and I add 2. But the input that we're evaluating at is maybe day 5 for the business model here. So what output do we have when we have a function depending on itself, depending on the input of 1? We're going to get 15 plus 2, or 17. So the output on that day, like day 2, or I guess this was actually day 1 originally, sorry. The output of day 1 for this nested function is 17 units, 17 cars, $17, whatever your business is, doesn't have to be business, but whatever your situation that you're modeling is describing. Okay, g of 0. That again, try it on your own. You should be comfortable with it hopefully by now. We're going to start with the g function as our outer function, the red one, and it's depending on the g function again, evaluated at the x value of 0. So we'd start with finding g of 0. Well, the g function was quadratic, right? It was 2 times x squared subtract 1. Feel free to write this out if you need to, but in your head, you would simply take 0, you'd square it, which is 0. Then you'd multiply 0 times the number in front, which is 2. But 0 times anything is 0. And finally, you subtract 1 from 0, which is negative 1. So feel free to write it out if you need to. That's a negative 1 for g of 0. Now I simply need to take g, the outer function, and evaluate it when x is negative 1. So let's do that. This is 2 copies of your input squared subtract 1. Feel free to do it in your head or write it out. This becomes negative 1 squared. Watch your sign. We make arithmetic errors if we go too quickly. Negative 1 times negative 1 is a positive 1. Positive 1 times 2 is positive 2. And 2 minus 1 is just, that's right, 1. So in this example, we've seen that we can take f of g, g of f, g of g. That's just ways that you can basically put one function inside of another, right? Those are the possibilities. Imagine, though, if you had multiple functions that depended on each other. It just makes your life a little bit longer and harder, but it's still the same concept. Okay, so we've evaluated at certain numbers, but what if we kept things general? Let's take a look at the next example. The next example says, find the function compositions if f of x equals x plus 1, so a linear model, but g of x equals x squared plus 4, a quadratic model. Okay, so to begin here, again, I recommend maybe color coding things. You don't have to, but I find it keeps me organized. So I'm going to let f of x be this red function, x plus 1, and I'm going to let g of x be this light blue function, x squared plus 4. So for the first part, f of g of x, remember what that means? Feel free to write it yourself with the parenthesis notation. That's right, you would say f, the outside function, depends on the inside function, which in this case is g of x. So now what do I have? I'm going to start with my outside function. So here's where we start. If it's generic, there's no number for x, but it's just generic. It's just x. this is where I want you to start. I want you to start with your outside function, which in this case says to do what? Take your input and add 1 to it. So my input adds 1. So because it's the f function, that's the rule I'm following. If it had been g out front, I would have said take the input and square it and add 4. So make sure you understand the idea here, not just going through the motions trying to follow me without understanding. Okay, so let's put in our g function since that's what we're depending on as the input here. Noticing before I actually execute this, if f is dependent on g, right, existing, then we would have to satisfy whatever restrictions in the domain for inputs that g of x may have. Does g of x have any domain restrictions if it's a polynomial? No, because it's all real numbers. There's no denominators or square roots to worry about. So we're going to satisfy g existing with any x value. So this is good news. Otherwise, our domain might get restricted. Now let's continue then, since we don't have any worries. We're going to insert g of x as our input for x in the outside function. So this becomes x squared plus 4 as the input for x here. And then we're going to add 1 because that's the rule for f. A lot of people right here get confused. Why am I adding 1? Because we are saying the f function depends on g as the input. So we start with the f function, which is take your input, add 1. So now just replace the input with the inside function g of x. Okay, maybe that makes more sense. You might need to watch that again until you really understand what I'm saying. What does this become? X squared plus 5. That's right. So when I put, look at what happened here. This is kind of cool. When I put a quadratic, which is a parabola, inside of a linear function, which is a line, I ended up with another parabola, didn't I? In other words, you can see that it looks like I just added the 1 and the 4, and I ended up with a 5 for its starting location, or the shift up that the parabola had. Okay, domain. Well, the result here is another polynomial. No fractions, so no restrictions on denominators, and no square roots, so you don't have to worry about a negative under there. So I would say my domain not only is no restrictions in the end here, right? This is a polynomial, so nothing to worry about for a domain. But also, the original guy, g of x, that I depended on, the inside function, also had this domain. So if they both have the same domain, you can say that's enough. Any of those x values is going to work, okay? But if one of them had a restriction, you would need to incorporate that into your domain. Try the next one on your own. Okay, so you started with g of x as your outside function. So you'd say g of something. But what's the something this time? What does it depend on? What's its nested function? F of x. Okay, so that would be f of x. Okay, so to begin, which function should I look at first? The inside or the outside when I'm dealing with a generic x? That's right, the outside is where I begin. So I'm going to say I want to start there. Always start on the outside. And the function here is g of x, the blue function, which said take your input, square it, and add 4. So that's what g of x tells us to do. So we follow the rule. Okay, but what's our input? Did you get f of x, which was x plus 1? So if you have this set up right, then conceptually you're understanding what's going on. You're inserting f into g everywhere you see an x. But at this point, it becomes a matter of showing off how good your algebra skills are. And a lot of students really need to remember what it means to take a binomial, 2 items, and square it. 2 items added together and square it. It is not the same as x squared plus 1 squared. That is not correct. It really involves foiling, and you can write it out or do it in your head. X plus 1 times x plus 1 is x squared plus 1x plus another 1x, which is really 2x, plus 1. So you need to FOIL here and get x squared plus 2x plus 1. So make sure that you have really strong algebra skills. Students who go on to pre-calculus and calculus and trigonometry and all the fun math courses for STEM majors, they have the most trouble with their basic algebra. So make sure that in this class, you are taking time to master those fundamentals. Okay, so now we have x plus 1 squared, we got that, but we're supposed to do the g function, which says take your input, square it, and add 4. So that's where I add the 4 at the very end. I took my input, I squared it, and now I add 4. So my final answer for g of f of x in this example would be that x gets squared, that you add 2x, and you add 5. In other words, we have another nice parabola in general form here. Again, polynomials have no domain restrictions because there's no denominator or square root to worry about. Additionally, f of x was another polynomial, which has no restrictions. So the domain would just be all inputs are possible, negative infinity, comma, infinity. Okay, I think we have one more to try. I really encourage you to do this one completely on your own. Find the function compositions for f of x equals the square root of x minus 2 and g of x equals 1 minus 2x. The first part A says f of x. So I'm going to write that out. Hopefully you tried it yourself and now you're just checking. As f, let me make f my blue function this time, depending on f again and evaluated at the generic x value, not a specific one. Okay, so what does this look like? Well, I'm actually going to make a note here. I'm depending on f, right? My function depends on f, which means that in order for f to exist, the inside function, the nested function, I would have to satisfy the domain of f, wouldn't I? Well, f is a square root function. So what would be the domain of f? What would his domain be? It would mean that x minus 2 could never be negative, right? So x minus 2 would have to be bigger than 0 or equal to 0. In other words, the radicand is always greater than or equal to 0. We learned this in a previous module in the course, so feel free to go back and talk about domain in your notes or videos. So this would mean that your x values that are appropriate inputs for the f function would only be x values which are 2 or higher, right? Add 2 to both sides. So the original domain for the f function would be bracket 2, comma, infinity, parentheses. Okay, so keeping that in mind, at the very end, when we list our domain of the new function f of x, we have to first satisfy the original nested function domain. So for example, maybe you get an answer that has a domain of x could be anything bigger than 0. But wait, in order for f to exist, the nested function inside, it had to have x values 2 or higher. So I would then take on that additional restriction and incorporate that into my answer for my domain. Maybe that doesn't make sense yet, but let's continue. Well, we're going to continue by remembering to start with the outer function. That's where we start. So the outer function says, take the square root of input minus 2. Input, I use parentheses, minus 2. Okay, but what is the input this time? That's right, the input this time is f of x, which was square root of x minus 2. Okay, this looks kind of funky. If you have time, I would encourage you to either go to Desmos and type this in yourself or your graphing calculator, or click on the link provided in the interactive notes online. What you'll notice is that this graph looks very funky. It kind of looks like a basic square root function, like a parabola on its side, but it's been shifted quite a bit. It's actually a square root inside of a square root. So we end up just with that answer. You could say the square root of x minus 2 minus 2. Now, I would strongly encourage students to put parentheses around the radicand x minus 2, the inside one, right? Because otherwise you might be, you don't have to admit to this, you don't have to raise your hand, okay? I wouldn't see you anyway. But you don't have to admit to this, but there's a lot of students, probably not you, right, who would just say negative 2 minus 2 is negative 4, okay? Can't do that though. If something is under a square root and something else is not under a square root, they are not compatible, right? We cannot go ahead and intermingle them, if you will. So this is our final answer for f of x. It's the square root of x minus 2 minus 2. And that's all under that first square root. Oh my. Okay, as far as answering the domain, not only does this answer have to satisfy the domain of the function we're looking at, but it also had to satisfy the domain of the interior nested function f of x. So what would the domain be for this really big answer? Well, we would say I need everything under the square root to be greater than or equal to 0. So what's under that square root? Well, the square root of x minus 2 minus 2. So it all must be greater than or equal to 0. That would mean that the square root of x minus 2 must be greater than or equal to 2. And how do we lift a square root? We square both sides. That's right. Might have been a while, right? That's just x minus 2 is greater than or equal to 4, or x is greater than or equal to 6. Why do you think that would be the necessary restriction? Well, let's go ahead and input 6 into this function. 6 minus 2 is 4. The square root of 4 is 2. 2 minus 2 is 0, and the square root of 0 is 0. Feel free to go through that again. That means that if I input 6, I get 0 as an output. If I input something bigger than 6, it's still going to stay positive. But if I inputted something like 5.9, that's going to give me a negative under the square root. So now we have this restriction. All x values which are above or equal to 6 are appropriate. Does that also satisfy the restriction for the original inside function, which said all x values 2 or higher? Well, which of them is more restricted, 2 or higher or 6 or higher? 6 or higher, so we take the more restricted answer. It's kind of like if you have two parents and one says be home by 10, the other says be home by midnight. If you have to satisfy them both, I know you probably would want to use the higher one, the midnight, but if you had to satisfy them both, you would have to be home by 10. So similarly, if I have two restrictions on my inputs, that x has to be bigger than 2 or equal to 2, but also x has to be bigger than 6 or equal to 6, I have to take the more restricted answer in order to satisfy both constraints. So 6 to infinity is our answer. All right, g of g. Did you try it yourself? If not, pause this video and try it yourself. Okay, g of g. Let's put it in red. That would mean I would say g depends on g of x, which in this case is a linear polynomial. Sigh of relief, right? No restrictions on polynomials, right? We love polynomials because they're continuous everywhere from left to right, and their domain is also negative infinity to infinity. So we have a situation where g of x has no restrictions on its domain, right? So we don't have to worry about that. But let's see what happens if I put g inside of g. That would mean my original outside function would be 1 minus twice the input. But in this situation, the input is g. So let's go ahead and input our g here as our input. And g said take 1 minus 2x. So we end up having a line inside of a line. Kind of interesting. Do the arithmetic very carefully, distribute accordingly. 1 minus 2 copies of 1. Minus 2 times negative 2x is positive 4x. And if we wrote this in descending order, which is typically how we write polynomials, I would have positive 4x subtract 1, or negative 1 plus 4x, same thing. So we ended up with a new linear function. And that is pretty common. If you put a line into a line, you get another line. In this case, though, the line is growing at a rate of 4 units for every 1 unit, instead of falling at a rate of 2 for every 1. So it has changed dramatically by inputting this line into itself. But notice that the domain is still negative infinity to positive infinity, because both the original nested function g of x was a polynomial, and so was the answer. The actual composite function is a polynomial, so the domain is still negative infinity to infinity. If you have time, I highly recommend typing in these graphs into Desmos or your calculator, or just clicking on the notes provided at the Desmos link, and you can visualize that your answer really makes sense looking at that graph. All right, so we've talked a lot about composite functions today. I hope that was helpful. Remember to practice, because math is not a spectator sport, and I'll see you next time.